Hello, everyone, and welcome to our presentation, a machine learning-based approach for predicting urban heat island growth in North Carolina's Research Triangle. I'm Catherine.
I'm Jacob.
And I'm Enzo. Now, before we jump in, here is some background information about the urban heat island effect. Now, the urban heat island effect refers to the relative warming in cities compared to nearby rural areas. This can be attributed to an increase in infrastructure, fewer green spaces, and higher population density. And as cities expand, an increase in built infrastructure often causes these urban heat islands to intensify. We wanted to understand how urban heat islands evolve over time in response to urban development and whether we could use measurable factors like land cover and population to predict that change. Now, our research question is, can the urban heat island effect be predicted using population and land cover data in the Research Triangle region using a machine learning-based approach? Now, rather than just identifying the factors contributing to urban heat islands, we wanted to predict how and where the effect may evolve in the coming years. When making this project, we had three key goals in mind: to build a machine learning model to predict land surface temperature, to identify key variables driving urban heat islands, and to forecast distribution for future years.
Now for the methodology.
To develop a generalizable model for urban heat island expansion, we first had to choose a study area with rapid urban change. As you can see on the map to the right, North Carolina has seen widespread population growth, especially in the central region. This is most evident in Wake, Durham, and Orange counties, which make up the core of the Research Triangle. What makes this region especially useful for our study is a high degree of variability in land use. It includes urban, suburban, and rural areas, allowing us to train a more nuanced machine learning model.
Now, in order to train our model, we had to first collect the data. We collected data from the Research Triangle for each summer between 2016 and 2024. This included 3 component variables and 1 target variable. The first component variable was NDVI, or Normalized Difference Vegetation Index. It measures how dense and healthy vegetation is in any given area. The second component variable was impervious surface percentage, which measures what proportion of land is covered by impervious surfaces, which do not allow water to transmit downwards. Our final component variable was ambient population, which measures how many people are in an area at any given time during the day. Our target variable was land surface temperature, or LST, which is how hot a surface is to touch. We retrieved all of these variables from readily available online sources, as you can see on the slide, with a spatial resolution between 30 and 90 meters across all variables. In order to process this data, we overlaid a 90-meter by 90-meter grid over the Research Triangle area and calculated the mean variable value in each grid square. Once we collected the data, we pre-processed it by normalizing LST and NDVI values across years. We used the data from 2016 to 2021 as a training dataset, reserving recent years as testing data. We then ran a random forest regression model on the data, which gave predictions for each grid cell in 2022 and 2023. Finally, data was extrapolated into 2024, 2025, and 2026 using a regression. We ran the model on the extrapolated data to predict future growth. Now for the results.
The model evaluated the expected relative LST value for each grid square in 2022 and 2023. As you can see, the model had an R-squared of 0.72 for 2022 and an R-squared of 0.71 for 2023, which is around 70% of the variance, indicating a moderately strong predictive capability. The root mean squared error, or RMSE, for each of these years hovered around 2, meaning that the model's predictions were within 2 degrees Celsius of the real value. The mean percentage error of the dataset was around negative 0.4 degrees Celsius, suggesting that the model tended to overpredict low LST values. Since there was a higher density of low LST values in our dataset, the overall model tends to overestimate.
So here are the predictive results as well. And we included actually one past year in 2024 in the predictive section as a baseline to check our model's accuracy. And as we can see, it tends to overestimate areas with low LST, but is otherwise consistent. The purple means lower, and you can see there's far more purple in the actual dataset. On the right, we can also see how each component variable changed over time. Impervious surface and ambient population tended to trend upward pretty consistently, but NDVI varied across years due to data inconsistencies, which is why we decided to normalize it.
What does all of this mean? With this strong predictive capability and small margin of error, our model has the capacity to relatively accurately predict LST values based on NDVI, impervious surface data, and population data, which fulfills the goal of our project. This project has many applications, including helping communities better prepare and design infrastructure for the coming years based on already existing city data.
Now, even though we would consider our project a moderate success, there are definitely limitations and future work that can be done in this area. So, a key limitation of the study was the constrained timeline of the NASA's program, which limited opportunities for the model's optimization, and also, as we mentioned earlier, the imprecision and yearly variability in NDVI and LST data. Future work in this area should focus on patching these holes and improving the accuracy of the model, as well as replicating it in different metro areas.
Now, looking back, working on this project was really eye-opening in showing how urban heat islands affect urbanizing communities over time. And we are eternally grateful to our mentors here at NASA for providing us with guidance and feedback in shaping our project. This project was particularly meaningful to me as my own hometown has faced more intense urban heat islands. Having witnessed this, it has been such a meaningful experience to work on this project and to gain a greater understanding of how urban islands change and intensify as time goes on.
Now, unlike Enzo, I haven't really observed the urban heat island effect firsthand in my own community, but I am really interested in geography, and I've studied the urban heat island effect. It's come up numerous times in textbooks and in competitions, and to be able to contribute to urban heat island research is one step towards maybe getting into one of those textbooks someday. And I really thank NASA Seas for providing me this opportunity.
Working with this team has been really fun. It's been an opportunity to get hands-on with the data and problem solving, but also work with different people from different walks of life and learning how to adapt. I'm grateful for that.
Now, here are a few of our sources.
With all of that said, we'd like to thank our mentors, Tanzia, Femi, and Dr. C, for guiding us through this project and offering very helpful critiques. And then, of course, thank you to NASA Seas for giving us this opportunity and providing us with the resources and the mentorship that we needed to complete this project. Thank you.